Hello, everyone. Today, I want to talk with you about one very hot topic, wireless power transfer. I will introduce some opportunities and challenges involved the research development of this topic. So my name is Xing Zhao, and currently I serve as a lecturer in the electrical engineering in the Department of Electronic Engineering, University of York. So I think it's quite straightforward to understand this topic, wireless power transfer, compared to the traditional power transfer use cables. If we do such a wireless charging thing, we can eliminate the power cables. This means we can, avoid some damages of the plug in and plug out. So, and also make it more flexible in some specific charging applications, such as EV charging and robotics charging, and also some underwater charging applications. So wireless power transfer, so I will not spend too much time in the definition of this research topic. So quickly move on to a simple history is this wireless power transfer is proposed actually in 1890 by the inventor Nikola Tesla. He tried to transmitting the power by some inductive and capacitive coupling, use some spark excited. Note it was reported by using the radio frequency and resonant transformers. Nowadays we call it as Tesla coils, and it can generate some high voltages. And later on, about in the 19th centuries, the inductive power transfer become the nearby wire coils was the earliest wireless power transfer technology that to be commercialized or developed. And since the transformer was developed in the 19th, we call it as induction heating. And it's first common wireless charging technology that was commercialized after the propulsion of this technology. And later on, a lot of research has done in this topic, from some small power application to the medium power, and then to the high power industrial applications. And I will just introduce some of my works involved in different power levels, and give some visions and research challenges in this research topic. The first work is about in the small power wireless charging application, and I try to, in the radio frequency and the long distance wireless charging application, the efficiency is still a challenge, normally lower than 50%. So how to improve the efficiency in the long distance small power charging applications? So we propose to use some metal materials. So as shown in this figure, and in this system, we have, it's a DC source, and we use an inverter to generate some high frequency AC voltage supplied to the transmitter coil. And it will generate some magnetic field, which was coupled in the receiver coil, and we use a rectifier to do some power transformation and supply the power to the low side. So it's a typical system for the wireless charging and coupled with the magnetic field. So what we do is, in the transmitter coil, we try to add some metal materials, and this figure shows the characteristics of the permeability of metal materials, and we can see in a certain frequency around 13 megahertz, and this metal material may exhibit the positive permeability. And if the frequency changes a little bit, it could exhibit the zero permeability, sometimes the negative permeability. So that means by design the metal materials with different frequency and permeability characteristics, we can try to control the magnetic field produced by the transmitter coil or of the wireless charging system. So what we do is, here we embed 4 mental material cores in the transmitter coil, and each one is connected to a resonant capacitor. So with the help of this mental material, we can see this. This is a result from the finite element simulation. We can see with the help of these mental materials, the magnetic field in the transmitter core side is enhanced. This means we can have a higher coupling effect between the transmitter core and the receiver core. And in this way, the transmitting efficiency can be improved. And we do some experiments, and we build up the transmitter core and the receiver core. It's shown in this figure, and we use vector network analysis to analyze the characteristics of the transmitter core. So the conclusion is with the help of mental material, the efficiency can be improved by roughly about 5%. So, however, we still have some problems. The thing is, this mental material is very sensitive to the frequency variation. So how to address this issue could be a future topic in our research. And another possibility is, what if we can try to realize some self-resonance WPT if we can integrate the PCB capacitance in the mental material design. And this is also a possibility to be explored. If we can realize such self-resonance in a high-frequency operation, we can eliminate the capacitance. So this could make the system more compact. So to improve the efficiency in wireless charging system, we can make some, materials innovation, and at the same time, it's a power electronics system. So what we can do is try to do some innovation in the power electronics side to reduce the conduction loss or switching loss, so that we can, the frequency of wireless charging system is very high. So that means the switching loss is dominant in some applications. So we try to propose some new power electronic circuits that can address the issue of high switching loss, and in this way to improve the system efficiency. And this is a topology we propose for a medium power battery charging system, and it operates on a low frequency at 85 kilohertz. And the innovation is, instead of using a 4-bridge inverter, we replace it with a dual half-bridge inverter. And in this way, we can reduce the current through each MOSFET at the same output power, so the conduction loss can be reduced. At the same time, we apply a new concept to replace the inductor using the variable inductor. So this figure shows the configuration of a variable inductor. We apply a DC coil here, which can control the saturation level in the magnetic coil. In this way, we can control the inductance in the core component. Why we need to do this? It's because with the changing of the low side, for battery charging, we need to achieve CC, constant current and constant voltage at different operating point. So that means the load is changing. So to maintain the good charging performance, we need to adjust the input side, and more specifically, we should adjust the inductance from the transmitter side. So that's the motivation why we try to apply such a variable inductor design, and the result is good, and we can observe by using the proposed dual half-bridge inverter with variable inductance control, we can maintain the good charging performance within a wide range of load characteristics. This is especially suitable for the electrical vehicle charging or battery charging, because the battery characteristics is changing with time, with temperature, and some other conditions. So this The third work is about dynamic wireless power charging. It's it's a hot topic, but until now it's still do not show some potential for the commercialization, because if we want to realize wireless charging, dynamic wireless charging, we need to embed a lot of costs in the roadside. This means the system cost is quite high. So even with such in-motion charging ability for electrical vehicle, it can reduce the size of onboard battery, or sometimes it can eliminate the onboard battery if we use some supercapacitors. But the system cost is quite high. So until now, the potential is questionable, but it's on the way. So this figure shows some two typical designs for the dynamic wireless charging. The first is in the transmitter side, we apply a single transmitter cord, and which is very long. And the second is we apply a segmented transmitter cord. So this one is, this one, to apply this one, we can analyze the transmitter cord one by one according to the position of electrical vehicle. This makes the magnetic field to, the linkage magnetic field is not so significant, but we need to apply a lot of control switches, and which is also, increase system cost. So another trend is what we can integrate the dynamic wireless charging with in-way motor. It's a very interesting topic, but the benefit is still questionable. So, and we see the University of Tokyo are still under developing of such wireless charging in-way motor, but overall speaking, the potential for commercialization is not so big. So the thing is, we try to develop some high power wireless charging from the different power levels with fixed frequency with 85 kilohertz, and the power can range from the 3.7 kilowatt to 22 kilowatt or even 50 kilowatt. So we should touch the high power wireless charging with innovation in power electronics and core designs. So finally, a short conclusion, and we have introduced some work in the material side, in the power electronics side, and introduce a concept of dynamic wireless charging for electrical vehicle. And we, as a conclusion, we see that the wireless charging are trending from small power to much higher power industrial applications to enable the electrical vehicle charging or robotics charging. So this is a quite interesting thing. And what we can do is we try to develop the high performance wireless charging equipment by using some new core design methods and some new power electronic circuit and control, and even the magnetic materials is also a breakthrough point. And we see some researchers try to develop some nano crystal flat bus and to replace traditional ferrite bus, which makes the wireless charging system more attractive. And we in the future we try to do some reliability analysis with electromagnetic thermal mechanical degradation, and also the foreign objective is concerned to maintain the reliability of wireless charging system. And the electromagnetic capacity and the safety become more and more important, and we should do more research on this part to enable safe charging of electrical vehicles, and to avoid a high magnetic field exposed to the human side. Another research point is omnidirectional WPT is on the way to enable autonomous systems. It's quite interesting, but not mature now. So that's all my presentations. Thanks.